Welcome back to Physics 141 online. I'd like to talk through some examples of problem solving using Newton's laws. First, we'll talk about drawing free body diagrams, and then secondly, important problem solving steps in order to use Newton's laws to calculate accelerations and forces involving moving objects. So, we clearly indicate forces that are acting on an object by drawing the object as a point particle and then drawing all forces as arrows away from the point in the direction of the force. We call this a free body diagram. Be careful on free body diagrams that you only draw arrows for true forces. Forces always are the kinds of influences where we can write that the force is caused by one agent acting on another agent. Note that velocity and acceleration are not forces. For example, if a block is sliding down an inclined plane and that plane is frictionless, this sketch shows the arrow indicating the motion of the object down the plane, and that's fine. But when we go to draw a free body diagram, we represent the block as a point particle. We draw in the surface of the inclined plane as a dotted line, and we indicate the only two forces that are truly acting on this object. The first is the force of the Earth pulling down on the object, and that's indicated by the downward arrow with magnitude mg. We also call this the weight of the object. Then the object resting or sliding on the inclined plane experiences a force that's perpendicular to the surface of contact, and we call that a normal force, normal being a synonym for perpendicular. In particular, notice that on this diagram there is no arrow pointing downward along the ramp because there is no such force. Be very careful in drawing free body diagrams that you only include true forces or interactions between objects. Now, for problem-solving steps, we will always follow these 6 steps when we set up Newton's second law problems. First, we'll always draw some kind of a neat diagram that includes important features of the system that we're studying. Secondly, we'll draw separate free body diagrams for each object of interest. And having drawn those free body diagrams, we will then choose a convenient coordinate system that will make analyzing the problem simple. And we can use different coordinate systems for different objects if we have a system that involves more than one object. Third, we'll write down Newton's second law for each object in component form, which means for each object there may be forces acting along both the y and the x directions, and we will have components for Newton's second law in each direction. Fourth, if we have more than one object, then we may very well have forces that appear in the 2 different free body diagrams that are related through Newton's third law. So we'll take advantage of that to provide additional information about the magnitudes of the forces. And then there are often constraint equations. When there's more than one object, those 2 objects may move in such a way that their accelerations are related to one another. They may be the same, they may not be the same, but they may be related to each other in some way that just depends on the physical situation and the way that those 2 masses are connected. So those constraints will often allow us to simplify the equations that we've written down before. 5. Count the number of equations you have and the number of unknowns. If you have the same number of equations as you do unknowns, then you have enough information to solve the problem. And finally, once you get the solution, we'll always check the answer for units, for plausibility, does it make sense, and for familiar limiting cases. There may very well be an angle, theta, in the problem, and so we might be able to check to see if the answer makes sense in limiting cases where theta goes to 0 or theta goes to 90 degrees. And here's an example that I'll just read and then pause the video and then solve using my sketchpad. 2 blocks with masses m1 and m2 are connected by a string of negligible mass on a frictionless horizontal surface. A force F is applied to m1 at an angle theta above the horizontal, causing both blocks to accelerate along the surface. Find the acceleration of the two blocks and the tension in the string connecting them in terms of the masses, the angle theta, and the force F. Here's the sketch. Now I would like to draw free body diagrams for the two masses separately. So we'll draw a dot for M2 on the left, and then we'll draw a dot for M1 on the right. M2, of course, experiences a force upward from the surface, and we will call that N for normal force, but we'll call it N2. It also experiences a downward force, which is the Earth pulling down, or its weight, M2G in magnitude, and then the string connected to it exerts a force to the right with magnitude T, or tension. Notice that the force F is not acting on M2, and so we do not include it. Now on M1, similarly, there is an upward force, the normal force, N1, the force F acting upward and to the right at an angle theta respect to the horizontal. The weight, M1G, and finally the string, which is connected to that mass, and so the string pulls to the left. Notice in these sketches that we put appropriate subscripts on the normal forces and on the masses in order to make sure that we didn't confuse ourselves and get symbols mixed up. In order to allow us to analyze the motion of this object using Newton's laws, and so the coordinate system can be indicated. Whoops, my stylus got completely off the screen. The coordinate system can be indicated conveniently next to the free body diagrams. There are cases where we might choose to use different coordinate systems for the different objects in the problem, but in this case it makes sense, since all of the forces except for the force F are horizontal and vertical, to just use the standard X and Y Cartesian coordinate system. So having defined the coordinate system, now let me write down the equations for Newton's second law along the X direction, because in this problem we're not asked to find any of the normal forces, and so we will primarily concern ourselves with just looking at the motion along the horizontal direction. So for mass M2, we will add up all of the X components of the forces acting on it and set that equal then to M2 times what I'll call A2X, because the acceleration is for mass 2 in the X direction. It's possible in some cases that an object might have acceleration components in two directions. So in this case, though, for mass M2, the diagram is very simple. There's only one force acting in the X direction, and so the left-hand side becomes T equals M2 A2X, and I'll just call this equation 1. We'll come back to it in a minute. We're not solving for T at this point because we don't know the acceleration. We want to find both that tension and the acceleration, so we don't have enough information yet. Now let's look at mass M1. We write down a similar kind of equation. The sum of all of the X components of the forces on mass 1, and let me go back up to the first equation and just put Fx2 there because that was for mass 2 to distinguish it from the X components of forces on mass 1. So that's equal to M1 A1X. Alright, now for mass M1 we see that there's a force T in the negative direction. There's also a force F. It's not along the X direction itself, but a component of it is. And so if we go up to the free body diagram, we can see easily that drawing a right triangle would allow us to determine that there is an x component which would be equal to f times the cosine of theta. Likewise, there would be a y component, f sine theta, but I'm not going to draw that. So what we have is a positive component of force, f cosine theta, and then we have a negative one because the tension force in the free body diagram is acting in the negative direction, and we have to be careful to put that sign in here. That's equal to m1 a1x. All right, I'll call this equation 2. Now, for the purpose of this problem, f and theta and the masses are all considered given quantities, so they can appear in our answers. But let me look at the equations here and count equations and unknowns. I've got 2 equations, but I have a1x as an unknown, a2x as an unknown, and t as an unknown. So I have 3 unknowns, but only 2 equations. And that's why I need one more equation, and you've probably guessed what this should be. We call this the equation of constraint because it has to do with how the motion of mass 1 is related to the motion of mass 2. They are constrained to move together so long as the string with tension T does not stretch. As long as it stays at a fixed length, then if m1 accelerates at a certain rate, so will m2. They move together, and they also both move in the positive direction. So we'll say that a2x is equal to a1x, which probably seemed obvious, but there are some problems where these constraint equations are not quite so simple. So now we have 3 equations with 3 unknowns. So let me just write that down. 3 equations, 3 unknowns. Remember, the 2 accelerations are the unknowns as well as the tension. And this is important because now, in principle, we can solve the problem. We have enough information to do it. How to do it? Well, I'm just going to take equation 1 for t and plug it into equation 2. So plug 1 into 2 because this eliminates one of the unknowns. So that means we get f cos theta minus m2 a2x equals m1 a1x. And now I'm also going to use equation 3, right? Use 3 to substitute in for a2x. This becomes f cos theta, and I'll take the m2 a2x and add it to both sides. So this is equal now to m2, and it was a2x, but now since I realize it's equal to a1x by equation 3, I'll just write that in. I'm trying to solve for the acceleration, so what I've got here is a way to factor it out because it's present in both terms. And so I'm ready now to solve for the acceleration by dividing both sides by the sum of the 2 masses. So a1x, and of course it's the same as a2x, is f cos theta divided by m1 plus m2. It's got the right units. I can check that because force is in newtons, which is kilograms meters per second squared, divided by a mass, which is in kilograms. So this would have the right units. It would be meters per second squared. We can check that out. So that's good. And then finally, we just want to take equation 1 and substitute in the acceleration into that. That will allow us to solve directly for the tension T. All right, remember, by equation 3, a1x and a2x are the same. So I can just sub right in. So T becomes m2 times the acceleration I've already found. m2 f cosine theta, try to fix the f a little bit there, divided by m1 plus m2. We can check the units. Mass in the numerator would cancel the units of mass in the denominator, leaving behind just the units of force. Force is in newtons. Tension is also a force, and so we get the right units. And in particular, there's one limiting case that we can consider. Let's imagine that the angle theta were equal to 0. So if theta is equal to 0, then that force F would be acting horizontally, and I could imagine the two blocks as forming a single system that would have the sum of their two masses. And what would happen then, we would get the acceleration value, a1x, that would simply be, since the cosine of 0 is 1, that would simply be f over m1 plus m2. And that answer makes sense, because it would be the really simple case where the net force F applied horizontally is the sum of all the forces acting on m1 and m2, and so the acceleration of the system would simply be the net force divided by the total mass. And that makes sense too. So we've been able to check our answers for dimensions and check our answers for a familiar limiting case. And I hope this helps in showing all of the different steps in solving problems using Newton's laws. I'll see you in class.